Inverse relations. Interchanging the first and second coordinates of each ordered pair in a relation creates the inverse relation. For a function f of x, f inverse of x, that is, f to the negative 1 of x is how we write that, is its inverse. Consider an original equation y equals x squared plus 1. Use the values x equals negative 2, negative 1, 0, 1, and 2 to create 5 ordered pairs for the relation. Then create the inverse relation using these coordinates. Graph the two resulting graphs, the original and the inverse. We begin, I'm going to make a table labeled x and y. My x values are negative 2, negative 1, 0, 1, and 2. Now the y values can be found by evaluating each of those individually into y equals x squared plus 1. So for example, I will take negative 2 in parentheses squared plus 1 to get my first value, and that happens to be 5. So my y values corresponding to the x values are, well, I'll just read the order pairs. Negative 2, 5. I have negative 1, 2. I have 0, 1, 1, 2, and 2, 5. I'm going to go ahead and graph these points. Okay, negative 2, 5. Negative 2, 5. Negative 1, 2. 0, 1. 1, 2. And 2, 5. Now my inverse relation will be interchanging the x and y, as we said. So that would be a table of y then x. And that would be interchanging those. I would have 5, negative 2, 2, negative 1, 1, 0, 2, 1, and 5, 2. So if I plot those points, 5, negative 2, 2, negative 1, 1, 0, 2, 1, and 5, 2. I'm going to connect these points in a smooth curve if I can. Same with the original points, my original relation. And there we have graphed the two resulting graphs, the original and the inverse. Using the graph on the previous slide, find the following information about the relation. I'm going to call it f, and its inverse, we'll call that g. So the domain of the original function was negative 2, negative 1, 0, 1, and 2, and that is a set containing those values. And the range of the original, that's our set of y values, so that is the set 5, comma 2, comma 1, and 2 and 5 are already included, so I'm not going to repeat those. The domain of the inverse was 5, 2, 1. Again, that's the set containing 5, 2, and 1. And the range of the inverse was negative 2, negative 1, 0, 1, and 2. Note the domain and ranges, there's a pattern here. The domain of f, I'll write that as the domain of f is the range of g, and the range of f is the domain of g. They are interchanged. As we said, we interchange the x and the y coordinates, so that only makes sense. Now, the line y equals x, you need to note something about that. these two graphs are a reflection across the line y equals x. We have symmetry. The graph in our next slide, shown below, is the graph of a function f. Sketch the graph of the inverse function. So what we have is it is connected 4 points. First point is -6, -3. Second point is -4, 2. Third point is 2, 5. And the fourth point is, let me say that again. -6, -3 is the first point. -4, 2 is the second point. 1, 3 is the third point. And 2, 5 is the fourth point. And it's connected by line segments. Now, to sketch this graph, on our graph, we already have the line y equals x shown. We'll interchange the x and the y components so that the point -6, -3 becomes the point -3, -6. I'm going to go ahead and plot that point down here. The point -4, 2 becomes 2, -4. And I'll connect those with a line segment. The point 1, 3 becomes the point 3, 1. And then I'll connect those with a line segment. And the point 2, 5 becomes 5, 2. Again, connecting those to the line segment. And so we have a reflection across the line y equals x.